There's a liquid that costs almost nothing. A liquid desert builders once used to raise 11-story towers from nothing but sand and clay more than 1,000 years ago. Towers that are still standing today in one of the most punishing climates on Earth. Not held together with steel rebar, not poured with Portland cement, not reinforced by anything sold in a modern hardware store. Built with mud, straw, and a liquid that every camel in the Sahara produces by the gallon every single day. A liquid so chemically unusual that modern researchers at some of the most respected institutions in the world have spent decades studying it, publishing the results in peer-reviewed journals, and then watching those papers sit quietly on academic shelves while the global cement industry continues collecting $400 billion a year. That is not a coincidence. That is a business decision. The liquid is camel urine, and what it does to desert soil at the molecular level is not folklore, not superstition, not some forgotten tribal myth. It is documented chemistry. Chemistry the construction industry has spent the better part of 2 centuries making sure you never ask about. This is the story of the oldest building technique in the Arabian world, and the reason the people who sell you concrete pray you never put these 2 pieces together. Before concrete existed, before Portland cement was patented in 1824, before any multinational corporation had a financial stake in what you built your house out of, the desert builders of the Arabian Peninsula were already solving an engineering problem that modern architects still struggle to answer. How do you build something permanent in a place where there is almost no wood, almost no stone, and where the temperature can swing 60 degrees between dawn and midnight? Their answer was earth. Compressed earth, layered earth, carefully mixed desert earth, and they stabilized it with whatever organic material their environment gave them in abundance: animal dung, plant fiber, animal blood. And in the deepest desert regions of what is now Yemen, Saudi Arabia, and across the ancient trade routes of the Arabian interior, they use the fluid produced in extraordinary concentration by the most available large animal around them: camel urine. The walled city of Shibam, in Yemen's Wadi Hadramaut, is where this story can still be seen with the naked eye today. Shibam has been called the Manhattan of the desert, and that nickname is not exaggeration. The city contains hundreds of multi-story towers built from mud brick and organic stabilizers, some rising 11 stories into the desert sky. The foundations of the city date back to the 3rd century. Its towers, many rebuilt and maintained through the Islamic period using the same ancient technique, have stood for centuries in one of the harshest environments on the planet. There is no steel hidden inside them. There are no synthetic chemical coatings. There is compressed earth, straw, wooden beams, and the accumulated knowledge of builders who understood exactly what every material in their hands could do. The city became the seat of the kingdom of Hadramaut in 300 AD, well before the Islamic expansion of the 7th century brought new waves of construction across the Arabian Peninsula and far beyond it. When 632 AD arrived, and the great movement of Islamic civilization began spreading outward from the Arabian heartland, the builders who moved with it carried this knowledge with them. The technique crossed the Sahara into North Africa. It pushed eastward into Persia and Central Asia, and it left behind a trail of earthen structures that still exist today. From the Grand Mosque of Djenné in Mali to the ancient clay city of Bam in Iran, every one of these structures was built using some version of the same stabilized earth principle. Natural organic additives mixed into raw desert soil to create something stronger, more durable, and more resistant to the environment than any of the individual materials could ever be alone. And this is where the science begins. Because what those builders were doing by observation, modern researchers have spent decades trying to understand and reproduce inside laboratories. And what they found is so inconvenient for the construction industry that it has been quietly pushed aside for the better part of a century. Let us talk about what camel urine actually is, not as a cultural curiosity, not as a strange desert tradition, but as a chemical compound. Research published in peer-reviewed scientific journals has documented something remarkable about camel urine that separates it from the urine of almost every other large mammal. Camel urine contains approximately 10 times more mineral salts than human urine, 10 times the calcium oxalate, 10 times the phosphorus. It also contains ammonium urate, potassium, sodium, magnesium, and a group of organic acids including hippuric acid and benzoic acid. Unlike almost every other animal, camels excrete only trace amounts of urea and ammonia, the compounds responsible for the sharp smell and high toxicity of most animal urine. What they excrete instead is a highly concentrated alkaline mineral solution, almost odorless by comparison, and remarkably stable. The pH of camel urine sits at around 7.8, meaningfully alkaline, closer to the chemistry of lime-stabilized soil than to the acidic urine of most mammals. And its density between 1.01 and 1.07 reflects how heavily loaded that liquid is with dissolved mineral solids. There is a reason camels produce urine with this profile. The camel kidney is one of the most efficient fluid conservation organs in the mammalian world. It evolved over millions of years to survive in environments where water is catastrophically scarce. The camel's renal system strips water from waste products to a level no other large animal can match. The result is a waste fluid that is not really like waste at all. It is concentrated. It is mineral dense. It is alkaline. Chemically speaking, it is much closer to a natural mineral solution than to the diluted acidic fluid most other mammals produce. What the camel body discards as excess is the byproduct of extraordinary biochemical efficiency. And it turns out that this efficiency creates something desert soils are uniquely prepared to use. Now here's what happens when that chemistry enters desert soil. Desert soils across the Arabian Peninsula and North Africa are typically calcareous. That means they naturally contain calcium ions, calcium carbonate deposits, and calcium-rich mineral particles. When a concentrated urea-containing mineral-rich liquid contacts that soil in the presence of naturally occurring soil bacteria, a process begins that scientists today call microbially induced calcite precipitation, or MICP. The soil naturally harbors bacteria that produce an enzyme called urease. Urease catalyzes the hydrolysis of urea, breaking it into carbonate ions and ammonium. Those carbonate ions immediately react with the calcium ions already present in calcareous desert soil. The product of that reaction is calcium carbonate, calcite, the same crystalline mineral that forms limestone, marble, and the shells of marine organisms. Dense, interlocking, stone-hard calcium carbonate crystals begin precipitating in the spaces between individual soil grains, binding them together from the inside out. This is not a surface coating sitting on top of the material, waiting to peel away. This is crystalline mineralization happening inside the matrix of the soil itself. The process fills pores. It bridges particles. It creates a continuous mineral network through what used to be loose granular material. The soil does not simply harden. It becomes something fundamentally different. Researchers at the Swiss Federal Institute of Technology measured the results of this process in bio-cemented sand samples and confirmed that the technique produces a material with documented compressive strength and stiffness comparable to natural cemented rock formations. A study published in Nature's NPJ Materials Sustainability Journal reported compressive strengths of 52.5 megapascals in biocrete produced using urea hydrolysis. For comparison, ordinary Portland cement concrete averages around 30 megapascals. The material produced through urea-driven calcite precipitation is not weaker than conventional concrete. Under optimized conditions, it outperforms it. And the ancient desert builders were doing something remarkably close to this process every time they mixed camel urine into their mud brick batches. Every time they kneaded it into their rammed earth walls, every time they soaked their compressed soil blocks in the organic slurry their camels provided in abundance. They did not know the mechanism. They knew the result, a wall that hardened and kept hardening over weeks and months. Bricks that felt light and friable when first formed, but became dense and resistant over time. Floors and foundations that, under the right conditions, seemed to turn into stone. And the key phrase is this, the right conditions, because the process requires calcium-rich soil, moisture, urease-active bacteria, and time. The desert environment provides all four. Calcareous, sandy soil is everywhere across the Arabian and Saharan regions. Moisture is scarce, yes, but it is present, especially at night, when temperature drops drive condensation into the earth. Urease-active bacteria are found in virtually all soils worldwide, with over 5,000 microbial species known to carry the urease gene. And time, in the form of weeks and months of curing under desert conditions, completes the transformation. Shibam's towers show what happens when this technique is scaled by master builders who refined it across generations. 11 stories of mud bricks standing in a desert wind, surviving centuries of floods, heat, and sand, still requiring only the same mud-based maintenance their original builders would have recognized. The city is a UNESCO World Heritage Site today, but what it is not is a blueprint the construction industry wants you to study too carefully. Follow where the money goes. The global cement market generates over $400 billion in annual revenue every year. Portland cement is the foundation of that industry, an industry built entirely on one idea, that building permanence requires an industrial input manufactured in a factory, sold in bags, shipped to your site, and purchased again for every new project. Cement does not renew itself. Cement does not improve over time. A cement wall weakens and cracks through cycles of moisture and temperature, requiring repair, reinforcement, and eventually replacement. From the industry's point of view, that ongoing degradation is not a design flaw. It is a feature. It is the mechanism that keeps the revenue flowing. A building technique where the primary binding agent is a biological process, catalyzed by bacteria naturally present in the soil, driven by a mineral input that camels and other animals produce freely, and strengthened over time as calcite crystallization continues, fits nowhere inside that business model. You cannot bag it and sell it at a markup. You cannot create a distribution monopoly around it. You cannot build a brand around something that happens in the ground when the conditions are right. The research exists, it is abundant, and it is credible. The MICP technique has been published in academic journals across civil engineering, geotechnical science, microbiology, and materials science. Studies from the Swiss Federal Institute of Technology, from university research programs across Europe, Asia, and the United States, all converge on the same basic finding. Urea-driven calcite precipitation produces a building material with compressive strength, durability, and water resistance comparable to, or even exceeding, conventional concrete at a fraction of the cost, without any industrial manufacturing input. The research has generated thousands of academic citations. What it has not generated is a single consumer product on a hardware store shelf. Not one. Because no corporation has a profitable way to sell you something the ground beneath your feet can produce on its own. The suppression is not a directive shouted from a boardroom. It is quieter than that. It is the simple, grinding logic of a market that rewards proprietary solutions and punishes natural ones. When the active ingredient cannot be patented, when the manufacturing process is a biological reaction that happens in soil for free, there is no economic incentive for any company to promote it. So it does not appear in construction handbooks. It does not show up in building code discussions. It is not taught seriously in civil engineering programs, despite being the subject of peer-reviewed literature going back decades. And the 11-story mud towers of Shibam are described to tourists as a charming historical curiosity, instead of what they really are, a working blueprint for a construction revolution. Think about what happens when a homeowner or a builder searches for natural alternatives to Portland cement. The first page of results is a wall of sponsored content from cement companies and construction product manufacturers. Branded soil stabilizers, branded additives, branded bags of dependency. And if you read the technical data sheets carefully, many of those products lean on the same basic mineral chemistry ancient desert builders achieved with freely available organic materials. The markup is not for the chemistry. The markup is for the packaging, the branding, and most importantly, the dependency. Every bag of proprietary soil stabilizer sold is a transaction that could have been replaced by a process that costs the buyer almost nothing. The industry knows this. That is why natural construction techniques are described in mainstream publications as impractical, limited, or suitable only for informal structures in developing regions. Not because the evidence truly supports that characterization, but because that characterization serves a market worth $400 billion a year. Here's what you can actually do with this, and we have to be honest about what it is and what it is not. This technique is not a replacement for structural reinforced concrete in a modern multi-story building. The ancient builders of Shibam were masters. They carried lifetimes of accumulated knowledge about soil selection, mixture ratios, curing time, and maintenance cycles. What they built was extraordinary, but it required maintenance. It required careful site selection. It required expert craft knowledge passed down across generations. What this technique absolutely is useful for is stabilized earthen construction. Foundations, floors, garden walls, compressed earth blocks, surface hardening for unpaved areas, and emergency building applications in resource-limited environments. At the DIY level, the process is more accessible than almost anything the hardware store sells. First, soil selection. You need calcium-rich sandy or silty soil. Pick up a handful, wet it, and roll it. If it holds its shape and has a gritty, slightly granular feel, you have workable material. Pure clay soils are too cohesive. Sandy soils from desert or arid environments are ideal. If you are in an area with calcareous soil, you already have almost everything you need. Second, the activating solution. Concentrated camel urine is the historical input, and where it is available, it remains the most mineral-dense and chemically suitable option. In practical terms for most users, food-grade urea dissolved in water at a concentration of 3 to 5% by weight produces a functionally equivalent activating solution. Urea is available from agricultural suppliers as fertilizer and costs almost nothing per pound. Dissolve it in warm water and mix it into your soil batch instead of plain water. Third, calcium reinforcement. In historically calcareous soils, the calcium is already there. If your soil is deficient, adding calcium chloride, available at hardware stores as a road treatment product for around $5 for a large bag, at a ratio of 1% by weight of soil, provides the calcium ion reservoir the precipitation reaction needs. Mix your soil, urea solution, and calcium source to a consistency slightly wetter than you would normally want for compressed earth. That extra moisture matters because bacterial activity needs a moist environment to continue. Form your blocks, tamp your walls, or pour your foundation layer. Then allow extended curing time. Not the 24 to 48 hours concrete demands, 3 to 4 weeks at minimum. And during that period, Periodically re-wet the surface to maintain the moisture level the bacteria need to keep working. What you will observe over that curing period is a gradual but measurable increase in hardness and resistance. A block that crumbles at the edges after 3 days will resist scratching with a key after 2 weeks. After 4 weeks, it will ring slightly when tapped. The calcium carbonate crystals keep growing inside the matrix as long as moisture and urea are present for the bacteria to process. The hardening is not complete in a fixed time. It is ongoing. Ancient builders knew this. They built their first stories and let them cure while the upper floors were still being formed. By the time the 11th story was rising, the ground floor was as hard as any natural stone formation in the region. The complete cost of materials for a basic urea-stabilized compressed earth project can run under $10, for enough to produce a wall section that no contractor using Portland cement would quote for less than several $100s. You cannot patent the soil. You cannot trademark calcium carbonate crystallization. You cannot build a recurring revenue model around a reaction that bacteria in the ground perform for free. The builders who raised Shabam into the sky understood something the modern construction industry has worked for 200 years to make you forget. The earth under your feet is not just raw material waiting to be processed into something commercially viable. It is already a construction medium of extraordinary capability, waiting for the right chemistry to unlock it. Chemistry camels have been producing for millions of years. Chemistry ancient builders discovered by observation, refined by practice, and encoded into structures that outlasted every empire around them. 1,000 years of mud towers standing in the Yemen desert is not an accident of history. It is proof of concept. And $400 billion a year depends on keeping that proof out of the conversation. The knowledge was never truly lost. It was only ignored. And ignoring something is easy when the people doing the ignoring control every hardware store shelf, every construction textbook, and every building code committee in the industrialized world. Now the knowledge exists in your hands, and knowledge like this, once it is in your hands, is not something anyone can take back.